But if it is processing error, I don't know what to tell you because we just did it. And no. No, that was a pain. I'm not starting over. All right, we are going to cover as much of chapter 4 as we can. Chapter 4 is input and output devices and motor controls. So for those of you that have had relay logic, we're going to kind of get into some relay logic. So we're going to look at the symbols. We're going to look at some sensors. We're going to look at indicators, and those are just lights, guys. And then we're going to see why we use them. I'm going to go through the objectives here. Push buttons and switches are also called discrete input devices. They either allow or disallow electric current to flow through them. So if it's open, it's not going to allow current. And the reason they say disallow and they don't say that it won't let current go through is because if you ramp up that voltage enough, you can jump the two and there's not much it can do. I can move wires apart from each other, and if I increase the current actually enough, I can get current to jump from one wire to the other. Okay. Do what? Yeah, there are some additional things that need to come into play or can come into play to know how much. But if I ramp it up enough, it doesn't have to have anything between it. It can jump. Yes, it is. I didn't say I wanted that it was a good thing. I'm just saying you could. But that's why they're saying disallow. They're not saying it won't let it. Okay. It can be physically changed to an on or off position. Just like that push button right there. If you push it down, the green one down, it comes on. And if you notice, the red one comes up. That one is interlocked so that they operate together. If I push a switch, this is a switch. I know it looks like a button, but it's not a switch. If I push it down, it stays there until I come back and push it the other way. That is a switch. Okay. All right. This, however, is a push button. As soon as I push it in, if I let go of it, it comes right back up. That is a push button. So it does not remain in that position until I'm through. So switches do, push buttons don't. These are the symbols for normally. NO means normally open. The top one is a normally open. The second one is a normally open held closed, which means that it's normally open, but I'm holding it, pushing it down, keeping it closed for some reason. You might have this might be a limit switch or something where you've got a load on it that's keeping it in that position. Or at the mines, this might be a limit switch where the little car that's carrying the coal might be loaded down, so it's keeping that switch down so that the car moves reverse to haul the coal back to the other side. I don't know, I'm making up stuff. Then you have a normally open push button. You got to push it down, and a normally open held closed. Normally open is over the top. We talked about this in the last one. Notice that the normally opens are all over the top. So this is not a normally closed. It's a normally open held closed. These are normally closed. Notice that all of the connectors are on the bottom. they are always closed until you force them open. So when I push a normally closed, I open it. So the normal condition of this one is closed. If I push it, I open it. We also have the normally closed, held open, 2 and 4. Everybody see that? These should be in your book. The poles are considered where the current enters the switch. They can be connected to movable contacts, and there can be several places where a switch opens or breaks the circuit. So basically with switches, we can have a single break or a double break. These are some alternate symbols for push buttons and switches. So we can have them connect one place, like here. It helps if I turn on my marker, doesn't it? So like here, if I close that one, it connects 2 lines, right? Well, on the other side, if I look at this one, I would have basically 3 lines. I may have one coming in here, one coming in here, one coming in here. So this could be like a selector switch. I could turn on this half over here, or I could turn on this half over here, depending on which way I throw the switch, but not both at the same time. Everybody okay? I'm not going to go through the rest of them, but most of the ones right now that you need to know are these top 2, or actually just this top one. And I'm sorry, this one. That's a single pole, single throw, single break, push button. We have momentary push buttons, and they're also latching push buttons. So if I push it down, I can lock it into place. And I wished I had one of mine from my pneumatics lab over here. But on those, I have a lock-in push button. I can push it down, and I actually have to turn it to get it to come back out of place. We have manual switches and automatic switches. So a manual switch means that I am a person and I manually reach out there and do it. Okay. An automatic switch is an electrical or electronic device. Depending on what kind of system we have, it could be an air device or anything else, but basically it's controlled by the system. So that switch would be activated by something else. So let's say we have in the mines, we have a small coal car, and we want it to go to the bottom slowly, go to the end of the track. When it hits the end of the track, we want it to switch directions and go back up. I could put a mechanical switch on the front of that thing. When it bumps into a plate or something, it hits that switch, which changes everything, changes the direction of flow, and sends the car back the other way. I could also put one on the other side of the car. When it gets to the opposite end, it hits the wall or whatever I've got down there. It mechanically hits it, flips the circuit, and it goes back the other way, and it could do that all day long. I could also set up an electronic switch, which would be something close to a diode. And when the voltage reached a certain level, it would trigger it and tell it to go the other direction. It's just easier to explain with a mechanical. We also have limit switches. And limit switches are, once it gets to a certain limit, it will open or shut off. A float switch. And if you've ever flushed a toilet, you have used a float switch. And it is an automatic switch because you don't have to tell it when to stop the water, do you? It runs water into the back until what? Until it fills up. And that float switch, whether it's a little thing like this or what, electronic or whatever, when it reaches its limit that it's set to reach, it shuts off. That is a normally open held closed. Now, how do I know that? The water holds it closed, and as soon as the water's gone, it goes back to its normal state and opens up, lets the water flow. The water rises, reaches the top, shuts it off again. Okay? So that's another type of an automatic switch. Switches, a lot of switches are designed to work in harsh environments. This makes it sound like all switches are. They're not. But there are switches designed to work in harsh environments. Industrial switches can be exposed to extremely high humidity. They can withstand liquid splashes in a lot of cases. They can, if they're designed to do so, they can handle gas and operate with gas all around them because, I mean, if you're working in a petro plant, you got to do something, right? They can handle dust, vibration, and electrical noise. So you can design a switch to withstand whatever you want to. We have temperature switches. And do I have any air conditioning students in here? No air conditioning students this time. Okay.
If you put your finger on a switch, what kind of switch is it? Like it senses like
I don't know.
is it like a pressure switch?
It could be. I'm not sure. I'd have to see the switch. What?
Yeah, like when we come out there when we hear it, so it's like soft, and you sense this thing, it automatically shut.
Yeah, that's actually a temperature switch. I think. I think that's. It's actually. I'm not exactly. You're talking about the salt. Is that what you're talking about? Oh.
Like where I work, it's like, you know what it feels like. There's like these plates slide, they stick the finger in a switch, and you sense it.
Do you actually push it down? It just reads your finger.
Yeah.
Okay. It's probably a touch switch of some type. So as long as you're touching it at all, it knows that it's there. There are some switches and things that are interlocks because they don't want you to be able to get your hands in things, and they force you to put your hand in two different places so they can't be in the middle. So if a punch comes down or a shear or something, they don't want your hands in it, so your hands have to be out here, and it won't operate until both hands are right here. I've even seen some that have interlock guides where you push a piece of metal in, and when you step on a foot switch, it pulls your arms backwards. So there's all kinds of safety switches. Pressure switches are usually hydraulic or pneumatic of some type. Now, realize that does not mean hydraulic fluid and air. Pneumatic is anything that's gas. So, and hydraulic is anything that's liquid. So it's just because it says hydraulic and pneumatic doesn't mean that it has to be hydraulic fluid and air. Okay. But a pressure switch senses the pressure and opens and closes for a determined pressure, either below or above that pressure. Liquid level, we just talked about liquid level, the back of the toilet. Flow switch is going to allow air or something to flow, to go through a pipe, and it could open or close depending on the flow rates. So you actually set the flow rate that you want it to have. Why am I back at float switches? Foot switches, you activate with your foot. guess what your gas pedal is in your car? It's a foot switch. It's probably, all of you know what that is, right? You push down on the gas and it gives it more gas the more you press, right? That is a foot switch. Well, guess what? So's the brake. The brake's another foot switch. Okay? That's also the same thing I explained just a minute ago, where they place them in factories so that you have to press a foot switch to let something happen, and they will put in environmental controls to grab both your arms and pull them back out of the way so you cannot put your hands in there. Okay, I'm either going backwards or something. Okay, proximity switches actually are going to use light. They use LEDs and photo transmitters, so you would have, you're trying to see if something's getting close. That's what proximity means. I know y'all have heard of the term in close proximity too. Well, a proximity switch is looking for something close to it. So if something gets close to it, it activates. If nothing's close to it, it doesn't work. Or it can be set up reverse, where if something's close to it, it doesn't allow it to work. So like a lot of the robot cages have proximity switches in there, or proximity detectors of some type. And so when you get near that proximity sensor, it knows you're too close to the robot and the robot will not work. The LED is a light emitting diode, and it actually is going to send out a light beam. The photo transistor is the receiver. So we send out a light and the receiver catches it, and you can actually set it up to break a beam, and that's another way of a proximity switch working. It's kind of like a photo detector or a light detector.
Like the light on the garage door?
Does it detect you coming in and out?
Break it, it stops the door from moving.
Yeah, then yes, it is. You're right. Yeah, I know what you're talking about. That's the safety switch to keep it from coming down on you, right? Yeah, if it's going up, it doesn't normally do anything. If it's coming down, it'll stop it in its tracks. We also have electronic sensors, and for the PLC, we can use the PLC to control or detect these and determine what we want to do with them. So I could have a proximity switch, and I can tell the PLC whether to activate this circuit or deactivate this circuit by the condition of the proximity switch. The PLC can act like our five senses. It can take those signals and convert them, and so it can, using those sensors, it can see, it can hear, it can feel, which it really can't, but using a sensor, I mean, what do we have? Those are our five senses, right? Well, that's what sensors do. An optical switch has light, and it sends out a light beam to something else, and if it's broken, it sees that something is there. Okay? If I set up an audio sensor and it hears noise and it turns on, then it hears, right? Even though it's only sensing vibration of noise, but it hears. I mean, our ears work by vibration, right? So it is, in essence, hearing. If I'm using something to know if I'm putting my finger on it to make it work, I'm using a touch sensor so it feels. So y'all see where I'm going from that? So in essence, the PLC, using all these sensors, can mimic our senses. So the proximity switch can detect existence of an object. We can use electronic signals to detect an object so that the object doesn't have to be touched, so it can just see the object as opposed to having to touch the object. We can have a state of whether it's true or false. And this is probably the way they do on that switch. If your finger is on it, it is true and it allows it to work. If your finger is not on it, it is false and it does not work. So going back to the ones and zeros, a lot of what we're going to do in sensors is it there or is it not? It's just a 1 or a 0. It's basically a digital. You don't have to know this. It's in there if somebody from industrial electronics wants to write it down, but it is not important to this class, so I'm skipping it. Okay. These are the optical sensors. Basically, it works like your eyes, but you have two of them. You have one that sends the signal and one that accepts the signal. Okay, but it can be very sophisticated, but you don't need to know all that because you're going to buy one. If you want one of those sensors, you'll buy the sensor. You're not going to build it. If you're in electronics and you want to build it, you'll learn it in another class. We have Hall effect sensors. I'm not going into all this, but these are used a lot in automated machines. They are used to complete the initial calibration and to detect the end stops. Okay, but other than that, I'm not really going to go into a lot. Ultrasonic sensors are hearing. It is the time required for the signal to move and come back. Piezoelectric. A piezoelectric is ringing the symbol, and I'm fixing to hit this desk, so, well, I thought it was. Vibration. So it's looking for the vibration of something to come back. So you're hearing the vibration of me hitting this. If I hit it over here, it doesn't work too well. But you can hear things vibrating over here. We have radar. We can use radar sensors. And most of y'all have probably been detected on radar speeding down the road. So you know what radar is. And you know that it can pick up speed, it can pick up different things, right? So we can use pilot lights for indicators. We can use a meter for an indicator. Most of what we use is a light. Is it on or is it off? And that's all we're looking for. Okay. Relays. We have magnetic relays. We have electrically operated control switches. Basically, in relay logic, this is a coil. I'm going to pass it around. I should just get you over here. Fine. That's what. Alright, here's the control relay. I'm going to start it over here so it ends up at you. Alright, so I'm passing around the control relay. Basically what a control relay does is it's a coil. And that coil can have two switches or can have switches off of it. So if I turn on this coil, then I can make this coil turn on something else. Or I can make it turn off something else. Okay? Or I can do both, actually. So a relay is nothing more than a coil. We are talking about relay logic, so no, up front. No, keep it going up front. I'm sorry, but I want it to end up in the back so he can put it back. In relay logic, we use those to turn things on and off. In PLCs, we don't have to. The PLC has those internal. So we can use as many of those as we want to. So that is one thing that motor controls you need to know. We don't have to have a physical relay. Basically, a contactor uses a small amount of electrical power to control the switch and to control a larger amount of power. So I can turn on this relay, this control relay with a small amount of power, but I can have it control a large amount of power. The magnetic starter here is 120 volts. Okay, so I can turn that on with 120 volts. But this motor that I'm actually controlling over here is three-phase. Three-phase, if I'm not mistaken. Yeah, 208 three-phase, or it can go up to 460, depending on how I wire it. So I can have 120 volts that I'm controlling, right? So this really would not be a large amount of current considered. But I can control 460 volts over here. Which is much larger. So I can control the small and activate the large. And basically this is the motor up top and this is the motor starter down here, the contactor coil, which is the motor starter. We also have solid state relays. I don't have any of those to show you, so I'm just going to continue on, but we do have, they do exist. A solenoid is nothing but a coil and a piston, a plunger. So if I put a voltage on it, the plunger goes out. If I don't, it stays in. It's real simple. It's used just for the movement. So I might have it to push something. Motor starter we've been talking about all day, so I'm going to keep going. Overload contacts. All of the motors have overload contacts, but one thing I am going to tell you is if you've dealt with motor control drawings, we don't put the contactors in a PLC drawing. I mean, the overloads don't go in the PLC drawing because we don't draw the motor. And when we draw the motor starter, we just draw it as one thing, so everything's in it together. We just draw a circle, that's it. There are also temperature overloads. These are the symbols for them. Magnetic overloads. And wow, we got through that whole PowerPoint. Can y'all believe that?